So thank you for the introduction. Welcome to my talk on efficiency of knowledge arguments in the D-log setting resisted. This is joint work with Max and Andy. And let me remind you of zero knowledge first. So in our setting, we view this more of interactive now. We have a prover and a verifier, and the prover wants to convince the verifier that some statement is true. For example, two ciphertexts encrypt the same message. And of course, we want completeness, so this protocol should succeed if both parties are honest. We want soundness, which means that a malicious prover cannot convince a verifier of a false statement. And in the interactive setting, we achieve this by the verifier sending challenges which a dishonest prover cannot answer. And finally, we want zero knowledge, which protects the prover. It guarantees that the verifier learns nothing except the truth of the statement. So there are many applications of zero knowledge, and the reason, or the main reason, is that it combines two properties, namely it allows to preserve privacy and secrets while allowing to attest to honest behavior. And one example is in electronic voting. So a simple voting scheme is you simply encrypt your votes in a randomizable encryption scheme and public key encryption scheme, and then shuffling party will shuffle these votes. That means it will permute the votes, and it will re-randomize the ciphertexts. And this will be handed to another party, which will then decrypt the votes. And now you've disconnected the incoming and outgoing vote by this shuffling. If one of the parties is honest, then this would work nicely. But there's one big problem. It does not work because if the shuffling party is dishonest, it could just replace all the ballots, all the encrypted votes with some of its own. So we need to ensure honest behavior here. But of course, we cannot reveal the permutation because the whole point of shuffling is that we do not know this connection. And here, zero knowledge proofs allow us to attest honest behavior while keeping the secret. We've also seen the application to anonymous credentials. I won't repeat this. Bulletproofs, not bulletproofs, zero knowledge. It's also useful in electronic payments. And you can even design or try to design provably secure ransomware. So what we did in our paper is we looked at shuffle proofs and electronic voting, and electronic payments that we looked at range proofs, which will bring us to bulletproofs. So let's have a closer look at range proofs. We're in a kind of commit and proof setting, though my terminology may differ from the previous talk. So we have a commitment, which is always this boxed value v, and it's a commitment to some scalar. And we want to prove that this scalar lies in some range, 0 to n, with n smaller than the modulus p. And use cases here are you can prove in eCash or in electronic payment schemes that you have enough funds to pay for a transaction. And the reason you want to do this is you can have arithmetic over and underflows, which is a really big problem because if you pay 3 coins and you only have 2, now you have p minus 1, which is a lot. This is the reason why range proofs are really useful and used in a lot of places. Now, the plan of action in the following is I'll first recall bulletproofs slightly different than in the first talk, because our proof system is very close to bulletproofs, at least conceptually. Then I'll sketch what modifications we did to bulletproofs, and then I'll have some details about how we did this. So let's recall bulletproofs. We're in a group setting. We have a group of order p, prime order, and we assume the discrete logarithm in this group is hard. And now some properties. First of all, the security assumption here is D-log, and if we want non-interactivity, we also want random oracles. We have an untrusted setup assumption, which is good. It's basically a random string. Our language, which we can prove natively, is R1CS. I'll talk more about this later. The proof size is logarithmic, which is also good. The proof of computation is n log n, and it needs asymmetric crypto. That's not so optimal, but it's good enough. The verify computation is in the same magnitude, order of magnitude as prover computation, which is not so good. So to summarize, the pros are we're in a D-log setting, which is widely used, and we have many primitives with which we can connect easily, like Elgamal encryption, Pedersen commitments, other Sigma protocols, and it's practically efficient. It's used in practice. The cons are, well, verification is expensive. There are some techniques to verify many proofs at once, but if you want to verify a single proof and it's a huge statement, it is expensive. And there are many alternatives. I won't go into any details, but you already saw some, and various trade-offs exist. So now let's have a closer look at bullet proofs and the tools. We also saw them, now different look at this. So bullet proofs need a linear commitment scheme, which in the case of the standard instantiation are just Pedersen commitments. And there you commit, your commitment is just one group element in size, so it's very succinct, but you commit to a whole vector of elements. And these commitments are linear. They allow you to add two commitments and get a commitment to the sum. And they also allow you to apply a linear operation, so a matrix to the commitment contents, but this matrix must be public. So this must be publicly known. And with this, we can build the inner product argument, which is the core tool of bullet proofs. And this was built by Bootle et al. And optimized by Binz et al. And this basically proves that given two commitments, their inner product is 0. And the important thing here is it's logarithmic in size. So this is where the succinctness of bullet proofs is coming from. And it's not zero knowledge. Yeah. So the language of bullet proofs, this R1CS language, has this form. It's a set of equations which allow one multiplication, but it's a multiplication of linear combinations of the witness or vector x. And this is basically the small sister of larger language quadratic equations, which are just quadratic equations. So you have constant terms gamma ij and all quadratic terms, xi, xj. And you can rewrite this in this inner product expression. So there is already some connection with inner products here visible. And now let's look at a maybe strange inefficiency of bullet proofs. That is, if you want to prove that an inner product is 0 for your witness W, then you can do this directly. You can't use the inner product argument. You have to go through R1CS. But then you need about n equations, and you need an additional n helper variables just to encode this, and you end up at a larger statement. And this is not so efficient as you'd expect, but why? And one reason is, yeah, of course, we have to go through R1CS. That's how bullet proofs work. Another reason is, well, the inner product argument is not zero knowledge, so we could not use it directly. So let's just imagine, what if we had a zero knowledge inner product argument? And in this case, let's try to use it. Let's be ambitious. We can try to prove a quadratic equation. And it's actually simple, right? You just prove it. And this, of course, does not work yet, because we want that x equals y. So I've been lying to you here. I'm lying all the time. All the details are different, of course. But we want to prove that x equals y. So we have to do this. But these are just more quadratic equations or linear equations, which are a special case of quadratic equations. So we can easily prove this too. And since we're in this commit and prove setting, we have commitments to x and y. This is the conjunction we prove. So this actually works. So now we can prove that one quadratic equation is true. And we can repeat this, of course. We're in this commit and prove setting where we can just prove conjunctions. And this is very inefficient, what I've explained now, because we need a lot of inner product arguments. But there's a very standard technique to make this more efficient, which is batch verification. So the verifier just sends random challenges, and we build a random linear combination of the quadratic equations. So we build this gamma as the sum random linear combination of the gamma I. And now the prover proves that this random equation holds. And if one equation were not true, multiplying it with a random scalar will make it a random addition to this sum. So it's very unlikely that the prover would end up with a statement which he could prove. So now we've actually designed we've done this, and we've actually designed a zero-knowledge proof system for quadratic equations pretty easily, right? And there's also another benefit of the zero-knowledge inner product argument, because we can easily get a kind of modular composition. Technical complications apply. This doesn't work like advertised. But we can also get a kind of modular composition, which is if we have a commitment to this scalar v, and we want to prove that it lies in the range of 0 and 7, we can easily do this if the commitment depends on the CRS of bullet proofs. So here the commitment is it's in this second component of the vector, and all the other components are, so the white components must be zeroed, and the blue component is randomness. We will ignore this. Now, to prove that this is, not to do this range proof, we make a statement which basically contains the bit decomposition of V, and we prove that it is in fact the bit decomposition of V, and this X looks like this. So we always require the first component of X to be 1, and we have randomness in the end, and then we want that the component, the orange thing corresponding to V, it must be 0. And then the gray boxes, they are arbitrary. They contain here the bit decomposition of X, of V. Now, as usual, the verifier sends us a random challenge. We do this, we combine this stuff, we get a new X prime, which is a randomized combination. And with this, we can now actually prove this range proof. Here we have to use transformed quadratic equations, so we have to undo this multiplication with alpha. But that's all we have to do, to use this witness V in X prime. And let's look at what happens if the prover is dishonest. For example, if he tries to put a non-zero value here at the place of V, then this will propagate due to the sum and the random linear combination. And when we undo this alpha multiplication in the quadratic equation, we get this additive alpha inverse term. So this will screw up the equation with very high likelihood, and the prover cannot do the cannot succeed in the proof. Now, this is also technical. Different settings need different constraints, and we may need additional proofs that things work out here. So this is just a simple example. But with this, we can already compare our construction with bulletproofs, and we share a lot of things with bulletproofs. So we have the same setup assumption. The proof size is almost identical. The verifier computation is almost identical. This led to some confusion because in the paper we have numbers of unoptimized verification. And in that case, since we use a different inner product argument, slightly optimized, our prover is twice as fast, and our verifier also. But once you use the delayed batch verification, then the verifier just needs one huge multi-exponentiation, and this is the same in our setting, so there is no difference in optimized verification. As I said, the prover is somewhat faster, so we expect about 25% speed up to hopefully remain after applying optimizations, because we do not know of any optimizations which you could apply in the prover setting. Our language is a strict superset, so we can prove quadratic equations, in particular our 1CS equations. And our construction is somewhat modular and malleable. And it's almost commitment proof, and as you saw, it's very easy to plug in this range proof there. And at least I had trouble with getting this modularity from bulletproofs, but from what I've seen, other people do not have this trouble, so I won't claim that bulletproofs are not very modular and malleable. So with this, let's have a small look at what I mean by modular and malleable building blocks. We start with this non-zero knowledge inner product argument, and then we get a almost zero knowledge inner product argument. It's not quite zero knowledge, but we don't need full zero knowledge, because we can then straight go to a quadratic equation satisfiability argument, which is zero knowledge. And yeah, so I'll skip this, or I say a few words. So we can explain the improvement of bulletproofs over the work of Boutel et al. By explaining the compression used there as simply a linear combination of protocols. And we use this technique also to obtain zero knowledge. And yeah, it's very convenient to view things like this, even though they may technically not truly be linear combinations. And there are also many variations for this almost zero knowledge inner product argument. We just stopped at almost zero knowledge because it was the most efficient compilation we found, and we wanted to be competitive with bulletproofs. But you can probably get full zero knowledge if you accept an additional round or something like that. Okay, so now I come to some technical details. So let's construct this zero knowledge inner product argument. So first, let's recall the non-zero knowledge inner product argument. The setting is the prover and verifier have these commitments to x and y, and the prover will split these into two halves and then send certain linear combinations or just additions of these halves to the verifier. And the verifier will then send a challenge back, and we do a combination of these halves like this, and now we've got a new statement, x new, y new, and we can recursively, we can recursively run this step until the statement is small enough so that we can just send the witness. Because remember, this is no zero knowledge, so we just want a very small proof. Sending the witness over has size n, we want log n. Here, our optimization is basically to see that we don't need this alpha inverse. It's just superfluous. We can use 1 there. And now you just save these exponentiations. Now, another improvement for the inner product argument is that we provide tighter proofs for extraction. And this modified inner product argument supports small challenges. Now, there are some technical problems because for exact security guarantees, you would need more analysis of the soundness error. But at least we're going in the right direction there. And if we can prove this secure with small challenges, we also get better proof of performance. So let's now have a look at how we turn our zero knowledge argument, our inner product argument, into a zero knowledge inner product argument. And the standard approach is we just add randomness. And this randomness is somewhat controlled. And since we have a logarithmic number of rounds, I'm skipping ahead. So what we need is we just need that every response of the prover looks completely uniformly random to the verifier. Then we basically get zero knowledge for free. And since we have a logarithmic number of rounds, we only need a logarithmic number of random components. And we will use this because if you look closer, you see that inner products are nonlinear. So we have a nonlinear propagation of the error, which is a problem, which we can solve by just requiring very, very nice randomness. We just say, well, we can pick the remaining n minus log n components so that the inner product of r and s is 0, the inner product of r and y is 0, and the inner product of x and s is also 0. And now we have no error introduced. So we just have the inner product of x and y being the same as the inner product of the noisy x and y. And with this, we get zero knowledge almost for free. Now, there is some drawback because the proofs get technical, and this is only almost zero knowledge because we have a certain dependency on x and y on how we can choose r and s. But as I said, in our quadratic equation satisfiability argument, we don't have this problem because we choose a good witness. So yeah, this is that. So I don't know if the construction of R is that interesting for you, but I'll go quickly over it. So you see that in very small instances, you just pick everything random. And once they grow larger, you just need to add 2 additional random blocks. So these gray blocks are random components in R, and the white blocks are just free. So we can use 0 there. And now we just need an additional 2, an additional 2. And we construct these so that in the recursion, where we add these half things together, this will happen like this. So these 2 blocks, these 2 half randomnesses here are added. And as you can see, or if you look closely, you see that you will lose 1 or 2 terms of randomness. In some sense, they will be burned because the verifier learns something in each round. So if we burn the randomness in the lower R2 here, we say that it's not random anymore, the verifier has learned it, then we end up with R1, which fits into the previous randomness mask. So this works recursively, and we get zero knowledge. And with this, I conclude. So we provide many small improvements over bulletproofs. The biggest improvement, in my opinion, is that we have a different understanding of the techniques of bulletproofs, which allowed us to get these quadratic equations instead. We provide simple and malleable constructions, so you can easily tweak them at a lot of places. And our language is more expressive, it's quadratic. Our prover's performance is somewhat improved. You can port this to some extent to bulletproofs. We have tighter soundness guarantees. We need similar results for linear map pre-image arguments, for those who know what I mean by this, because we need those for the shuffle proofs. And actually, those are the basis for the inner product argument. So it's what I present is the other way around. And lastly, we have some open questions, namely, is there quadratic equation-friendly crypto which provides non-generic speedups? So by generic speedups, I mean we can prove matrix-matrix multiplication basically without overhead, because each term of the matrix-matrix multiplication is just an inner product, and you get this for free because an inner product is a quadratic equation. But are there specialized primitives which work especially well with quadratic equations? So we're now experts in cryptanalysis, and yeah. So with this, I'm ready for questions.
Questions?
I may have missed something, but what does more expressive mean here?
You can, I mean, a quadratic equation expresses, it's just a superset of R1 CS. That's what I mean by more. So, okay, maybe this is badly formulated, but I can express a quadratic equation in one native thing, whereas I need many R1 CS equations perhaps to express one quadratic equation. So okay. The inner product is one example where you need a lot of equations.
I see. Thanks.
Yeah, so my question is about the relation with the first paper, because they also used like an inner product argument based somewhat on bulletproof. I mean, a more generic one, which also worked for group elements. But if you only look at the inner product argument for field elements, do they use similar techniques, or are you
I'm not familiar enough to know. I would expect that the techniques translate to some extent, except for GT elements. There, I don't know.
Other questions? Right. In that case, let's speak you again.